it's up to you to show in some way that what you've done is correct. And that's the way we, when I was in school, that's what I learned. But recently, it seems like that's changed. And I couldn't find the exact quote, but I know that Hal Abelson has said, you know what, software has become a natural science. Because what we don't do anymore is sit down and write a routine from scratch and prove that it's correct. Instead, we go on GitHub and we download something, and it's a natural object, and then we try to form scientific theories about it. And some of the theories we get from reading the documentation, but we know those theories might be wrong. So instead we do experiments on it. Here's a piece of software, when I poke it like this, I think it's gonna react like that. Okay, my theory's correct. Oh no, my theory is wrong, I have to update my theory. Not by proving it, but by trying stuff out. So that's changed the way we look at software. And maybe it's a good place for more of an opening of these kind of softer techniques, and a good place for machine learning to fit in. So what is software? You're given a specification of some function, and you implement the function that meets the specification. And there's other parts to software too, but that's what we're going to concentrate on. And how is that different from machine learning? Well, one type of machine learning, you get some example input-output pairs, and you try to guess a function that matches those pairs well, and that will also generalize well for novel X that you haven't seen before. And of course, there's other kinds of machine learning too. Now, what's deep learning? Well, for this audience, you all know that, but I'm going to go over it anyways. So it's a kind of learning where the representations you form have several levels of abstraction rather than a direct input to output. And there's other kinds of deep learning too. So now the caricature you get is we've thrown away the software engineer in the middle, and instead we have a machine learning system, and the data comes in, and a representation comes out, and that representation looks something like this. So it doesn't look like code, it doesn't look like the clean boxes of components, rather it looks like a huge pile of parameters, and at different levels, maybe if you have a good intuition and a good theory, you can kind of make sense of what's going on at different levels. So you expect that for this image recognizer at the beginning levels, you expect to see lines, and then components of lines, and then faces, and then entire scenes, and so on. And of course, deep learning's really hot. You can see the graph. I don't know how well you can read that, but it starts in 2005, going up to 2015, and it's really taken off in the last couple of years. This is the Google Trends search for the term deep learning. I thought it was interesting that there's such a spike in 2005, because traditionally we're told that it started all in 2006 with this paper by Hinton and his team. But apparently there were preprints or something, or some other stuff going on in 2005 as well. You can also ask Google Trends, where are these search terms popular? And look at that. North America and Europe don't even make the list. South Korea is where it's popular. Now, why would that be? Anybody know? Yeah, there we go. So if you add the search for Lee Sedol and AlphaGo over the last couple of months, that's almost matches the numbers for all of deep learning. So a lot of interest there, and we'll talk a little bit more about that later. So I want to talk about machine learning as an agile tool in software engineering. So now the picture is more complicated. You have the data and you have some idea, and then there's still a person in the loop. We haven't gotten rid of the person completely, but now the person's not quite a software engineer. Maybe a data scientist is the right word for him or her, but somebody in the loop who's operating on the ideas and the data and the feedback from machine learning algorithm. So now the question is, what is it that we're going to be able to learn? And we're going to go through a bunch of examples. So can we learn functions from examples? Well, yeah, that's the bread and butter of machine learning. And here's the simplest example. You have a bunch of points, And can you learn a function that fits it? And in high school you learned how to fit a straight line. And now we've learned that there's more sophisticated things you can do. And you can have other types of X, Y, or Y pairs instead of just points in a plane. So you can have sound waves and do speech recognition. You can have images and do image labeling. And you can have sentences in one language and translate them to another language. And all that works pretty well. So the answer is yes. For many kinds of functions, we do know how to do that. Now, can we learn parts of programs from examples? And here's, about a decade ago, this really struck me that this is one way to do Agile software engineering. When I was looking at this open source spelling correction program, which is a very nice program, but it's over 2,000 lines. And there's still some stuff it doesn't get right. So here's an example, and this is in a commercial product, a word processor that some of you might have seen. And sometimes when you type into it, and little red squiggly lines show up, even though I have spelled the name of my colleague correctly. But because it's using a dictionary to do its spelling correction, his name doesn't happen to be in the dictionary. And so it alerts that those aren't words. And if you ask to correct it, it suggests Tehran salami, which is not accurate. But if you only have a dictionary, that's probably the best way to do it. So, of course, web search engines and other people say, well, the dictionary isn't good enough. Instead, let's use all the words we can find on the web. But then those aren't correct, so we have to have some way of figuring it out. And basically, you apply a naive Bayes learner. And here's a simple one, which is only 17 lines. So we've gotten more than a factor of 100 reduction in the number of lines it takes, and the performance is just about the same. So that seems like that's nice Agile software engineering, and then the result is you get something like this where it gets the right answer. So can we do more of that? Here's another example. So this is a block diagram of the machine translation system where each of these components is coded by hand, but there's lots of parameters that are learned by machine learning systems within them. So now it's sort of a partnership between human programmers that put in the structure and machine learning algorithms that flesh that out. Another example is AlphaGo. So this Go playing program where it's not quite a deep learning network that goes all the way from input to output. Rather, there's a structure to it. So the programmers said, we're going to have zero in a policy network that says, let's figure out, let's learn a function for the probability distribution of the best actions over any given state, and a value network that says, how good is this state to me? And then on top of that, there's a search mechanism that says, let's look forward as far as we can and apply these to figure out what the best move is. And so there's a structure to the program that's written by hand, and then all the parameters are learned. And people have talked about how important this is as a milestone in the history of AI. My friend Gary Marcus wrote this piece on Medium about the chasm hasn't quite been crossed yet, and I teased him because The Onion made pretty much exactly the same point that he did. So Tiffany Wells is not a well-known AI scholar, and this may be a pseudonym because I think I've seen her published under different names as well. Said that's not fair. Using a combination of complex algorithms to aid reinforcement learning is cheating. Right? And so that's the same point that Marcus was trying to make, that it wasn't all learning, that there was some other stuff thrown in there as well. So can we learn parts of programs from examples? Yes, we can do that very well. So if we have a structure, the human programmer has figured out mainly what to do, and we want to fill in some of the parameters, we have lots of good techniques to do that. Now, can we learn entire programs just from examples? So now it's getting more interesting. And there is a long history of many decades old in this idea of program induction. And for the first 4 or 5 decades, we worked all on simple examples. So here's an XY pair. If the input is the list 3, 2, 1, and the output is 1, 2, 3, and here's another example, the input is the list 0 and the output is the list 0, what program can you induce that would generate those and generalize well to other things as well? Well, I can think of at least 2 programs. Here they are. And so one of them is the reverse program and the other one is the sort program. And there are techniques that would generate these well. And then if you gave it that one more example, then it would choose the reverse function. And if you gave it that example, then it would choose the sort function. So that works fine in these kind of 2-line up to maybe 5-line programs. You can actually get those to work well. In the 1980s, we did that with logical and functional languages, sometimes with genetic programming, sometimes with inductive logic programming. And it never got past these 5 or 10-line programs up towards what you really want to be able to do. In the 2000s, we made a little bit of a jump, part because there's more computing power, and partly because we made the representations better. So started doing based on probability rather than logic. So now you can zero in on the most likely programs rather than having to consider all possible programs. And then more recently, there's some of this deep learning and LSTMs and more complicated intermediate representations. And some of the tricks are using languages in which there's only one way to do it. So if you're searching the space of all possible programs, and x plus 1 and 1 plus x are both expressions in your language, you don't want to double the search space. So you can have a language where, say, x plus 1 is a legal expression, but 1 plus x is not a legal expression. So those sorts of tricks. Stronger type systems seem to help. Total functional programming, so that's only allow recursion that you can provably terminate. That eliminates this halting problem. And it also seems to work well on domain-specific languages. So, for example, trying to synthesize regular expressions rather than trying to synthesize C++ programs is simpler and gets farther. Okay, so that's one line of work. But another line of work is saying, well, let's, trying to generate a program like a human generated, why should we bother doing that? Let's just generate parameters and call them the programs. So can we do that for things like this machine translation system? So rather than say, can we one at a time optimize each one of these boxes that was written by a human, can we say, let's throw all those boxes out and replace the whole thing with just one deep net that goes directly from input to output rather than going through the steps that the linguists/programmers thought were the right thing to do? And the answer is yes. In fact, you can do that. And you can pretty much duplicate about the same state of the art as these complex translation programs just by feeding in examples and having it generate everything all by itself. And you can read that paper. Another example is playing these Atari games where the input is just experience playing the games. I didn't have time to get the connection, so I can't show you the video, but it starts out playing really poorly, and then after a few thousand turns starts to get the hang of it. And then for, I think something like 3/4 of the Atari games plays at human level or better. And the games for which there's a long-range planning component still doesn't do quite as good as humans. So if you only have to think ahead a couple of seconds, it does great. If you have to have a long plan of, I'm going to go all the way down this corridor, and then go up into the corner, and then come back, it tends not to do too well in those types of games. So it's this typical convolutional net type program where the input is all the pixels, and we look at fields of the pixels at multiple levels. I should say that one thing that some people miss is that it's also the score is given as a separate input. Now, they could have made the system figure out that the score is displayed in pixels on the screen, but they thought that would just slow things down for no good reason. So they fed in the score as a separate input, so it wouldn't have to learn to read that. And so can we learn entire programs from examples? I don't know what to say about this for sure. So yeah, if it's a short functional program like the sort program, we can learn that. If it's a deep learning network, there's lots of cases where it works really well, but we don't quite understand the boundaries of where it works and where it doesn't work. If it's a 10,000 line C++ program, nobody knows how to do that yet. So I found this nice quote from Jan LeCun talking about what these different techniques are. He says, if intelligence was a cake, then unsupervised learning would be the cake, and supervised learning would just be the icing, and reinforcement learning would be the cherry. So what he's saying is the world is not like an Atari game. You don't get a little score up in the corner that tells you how well you're doing. And so don't rely on reinforcement learning to do everything, because most of the time you're not going to get those reinforcement. And most of the time you're not going to get supervised examples. Most of the time you're just existing. And that's where we do the worst. So he thinks we still got a long way to go. Okay, so why is learning entire programs hard? Let's go back to our senior figure in the field. Dijkstra said, in the discrete world of computing, there's no meaningful metric in which small changes and small effects go hand in hand, and they're never will. So what he's saying is you have a program and you change one bit in the program, that could be a completely different thing. And there's no way you can make it so that changing one bit in a program will have a small effect on that program. Here's another senior person who says, when a distinguished but elderly scientist states that something is possible, he's almost certainly right, but when he states that something is impossible, he's very probably wrong. So maybe we shouldn't take Dijkstra too seriously. And another one of my heroes, Ken Thompson, says, when in doubt, use brute force. So here's a fascinating attempt to do this. Neural Turing machines. So what's a neural Turing machine? So like a Turing machine, it's got a read and a write head, except instead of just reading an individual bit and writing out a bit, it has this convolutional field, and it reads over that field, and you now have the property that you can differentiate it, right? So Dijkstra objected that you change one bit and you made a big change to the program. Now, instead of having bits, we have real numbers. Instead of having individual ones, we have a neighborhood of them. And that objection goes away. So you now have a program where you can make a small change to the program, and you get a small change to the effect. So just to refresh your memory, in this audience, probably you guys all know this. We want to find, in regression, we want to find a function to minimize the error. And the error is a function of the empirical loss, how many things you get wrong, and the generalization loss, how complicated is and therefore bad do you think this function is. And then we just sum that up over all the examples. And when we do that, we can do this gradient descent. And in convex optimization, this is easy. So this represents the loss surface. So if you're trying to fit a line, y equals mx plus b, or in general, you have two different parameters. You search on this space of parameters, and that gives you an error. And if you're over here, your error is way up there. If you're over here, the error is there, and you want to get somewhere in the middle where the error is low. And for some formulas, you can solve that analytically. For more complex ones, you start up at the top, then you start making steps downhill, and if you start here, you end up over there, and if you start here, you end up in a different place, but they're probably both pretty good solutions. So the problem with a traditional program, a Turing machine or a C++ program, is it's non-differentiable, so if you change one bit, you made a big change to the program. But with these neural Turing machines, now we have this possibility of saying, I'm gonna make a small change, I can go downhill, I can reduce my error, and maybe I'll end up in a good place. And it can do things like functions like copying the input to the output. It can sort of do things like sort, although it wasn't completely convincing that it's going to get that right every time. So, don't rely on this to get anything done, but it's an interesting point to think about. Now, I guess my reaction to it is, okay, so you've made these functions differentiable, but to me, the space that we're dealing with looks like a porcupine, right? So we've taken each of these quills at the spike of the porcupine, and if it was a binary program, that would have a flat top that drops off on either side, and now we've taken a file and we've made it the top rounded. So it's not a 0-1 drop-off, it's a round drop-off, but there's still a bunch of spikes. That's the way it looks to me. So this doesn't seem all that promising to me. And today, we can't really get very far with this approach. But who knows where we're going to be able to get to. Now, I want to take one little side trip. So this is not really about machine learning, but this is another way to think about how we specify programs and what we can do with them. So here's a paper by Franz Ock and his advisor, Ney, about machine translation systems. And you can read the whole paper, but basically you can see that there's two key formulas here. It doesn't really matter too much what they say, but this is half a line and this is half a line. So we have these 2 lines of math, but that translates into thousands of lines of C++ when you go to implement that. And so what this paper was talking about was the alignment problem. You have a sentence in English and a sentence in French, and you want to know which words correspond to which, and that was solving the alignment problem. And here's a list of available packages, and the one that does that is 16,000 lines of C++ to implement those 2 lines of math, right? So that's a bad ratio. And but it's necessary because you want the program to be efficient. There's all this stuff you have to do. You have to read the files in. You have to break them up into words. You have to store them and cache them and all that stuff. So I'm not saying those guys did a bad job. That was probably the best program you could write. But you'd like that process to be faster. And so we're starting to see some of these more declarative languages that allow you to write something more like the math, but have it execute efficiently. And this is Jason Eisner's approach, and there's sort of half a dozen of these. And so this is a different task, not the alignment task, but this is the natural language sentence parsing task. And you get to write these just sort of declarative statements. And so kind of these lines define the whole parser, and then you would have a lot of these lines, one for each grammar rule and one for each word. And then you'd have a parser, and the system would automatically make it efficient. Right now, these systems, and some of these can be extended in various ways. So this is a relational language, kind of a prologue-like language, where you don't really specify the control flow, but you just say what's true. Some of them are probabilistic as well. And I think the lesson is, these look pretty interesting to me, and I think more of what we do will be done in these types of languages in the future. But they aren't there yet, they aren't mainstream. They don't really learn that well to execute efficiently. It's more like, they're more like compilers than like learning systems. And we'll see how this develops over the coming years. Now, I thought the neural Turing machine was fascinating. I wanted to go into one more really interesting paper. Can we learn an interpreter? I would have never thought the answer to that was yes. But here's a paper, learning to execute using a recurrent neural net with long short-term memory. So what does that mean? So it means that we give the system input-output pairs. So the input is a program like this, and the output is a target that would be printed by the execution of this program. And that's all we give it, right? So we don't tell it anything about the structure of this programming language or the structure of integers or if statements or expressions or anything else. This is just a sequence of characters, and it has to learn basically how to parse this, how to figure out what the arithmetic expressions are, how to execute the program or somehow figure out what the output of the program should be. And you see here, well, it gets 2 out of 3 right. This one, the correct answer was 25011, and the answer it came up with was 230111. So got 2 out of 3 right, or every digit except 1 right out of however many digits there are. So fascinating result, right? So you think, well, this shouldn't be possible because this was done with a neural network, and it's only got so many levels in it. But a program could potentially be any depth recursively deep, so it shouldn't be able to represent that. And I guess one way to think about it is, well, yeah, but it probably can't, because all the programs that were generated were sort of this type of template. So you initialize 1 or 2 variables, you do a loop a certain number of times. Within that loop, you update a variable, and then you print some expression. And so I think what's happening is basically every output is a quadratic function of these inputs. And so it doesn't have to learn to execute the program, it just has to learn to recognize which quadratic function is this. And if I allowed the target functions to be any program, it would do worse. But it's amazing that it does as well as it does. So can we learn an interpreter? Partly, but that's not the point. The point was not, let's throw away your interpreter and replace it with this. The point is, these networks can do things that before nobody would have thought or would have tried for them to do. So this is really just an exercise in saying, let's open up your minds and say, something else that you thought would never have worked, well, maybe it will work. So here's an interesting one. Can we learn a user's language? So far we've been talking about generating things in formal programming languages or generating sets of parameters. Can we understand what the user's language is? Well, we did that for natural language when we tried to do the translation between French and English. Can we do that in formal or semi-formal languages as well? So I had an interesting conversation with Wolfram about his Wolfram Alpha, and we decided that Wolfram Alpha is kind of halfway between a programming language and Google. So in a programming language, if you get 1 semicolon wrong, you don't expect any output. And you say, that's an error, that was my fault, I don't get anything good out of it. When you type something into the Google search box, you say, no matter what characters I put in there, it's got to come back with something. And Wolfram Alpha is kind of right in between. So it doesn't have a formal language. It accepts all sorts of different things. And the Wolfram Alpha engineers are looking over their logs every day saying, well, what is this language that our users are using? And can I implement that better? So here's a great example. If you say x up arrow 1/2, then Wolfram says, okay, that's the square root of x. If you say x up arrow 2/2, then Wolfram says, okay, that's x squared over 2. Right? So there is no fixed precedence. Rather, it's these Gricean maxims that it says, well, what was it that you probably meant? And that's what we're going to interpret it as. We're not going to have any fixed meaning. It's we'll go by what we think your intent was. And so that's fascinating. Can we have more of our formal languages like that? I'd like to see the programs I interact with understand my intent better. One of my pet peeves is you've got some app on your phone and you press a button and nothing happens. And how many of you then press that button harder? I know I do, right? And what happens? Nothing. Well, that's dumb, right? If I wrote one of those apps, I would say, if somebody really jammed that button 3 times, the 3rd time I'm going to do something different. Maybe I can't really solve this problem, but at least I'm going to say, hey, I'm sorry, I can't do that, and here's why I can't do it, or here's something else you can try. But don't just sit there and do nothing.
Say ouch.
Yeah, say ouch, do anything. So can we use the user's language? Well, that's an interesting idea. So far it was done by hand, so I said, Wolfram Alpha can do this, but they don't do it by machine learning, they just do it by engineers looking at the logs and saying, here's what I think our users are doing. But it's probably a good application where machine learning could respond well. Here's something I've been working on for the last couple of years, is tutoring from examples. And here's an example, so this is a Python program. You say this and it says syntax error. So not very helpful. And now you say this, and it says syntax error, invalid syntax, and indentation error. And what it really meant was you're missing a colon, but it didn't say anything close to that. So users get really confused with these syntactic errors. Users also get confused with semantic errors. So here we're going to follow a beginning student trying to write this program, and was very clever here and said, okay, I have 3 lists and I want to initialize them all to the empty list. So I'll do this, because I know you can do this kind of assignment. And then it says, no, that's no good, because the left-hand side has 3 things and the right-hand side has 1. And so next, the student was very clever and tried that. And now it doesn't complain. It says that's syntactically valid. But what happens is those are all the identically equal list. When you append to one of them, you're appending to the others, and bad things happen. And it took a long, long time, and I won't go through all the intermediate steps, but eventually the student came up with a good answer, right? But we didn't give them any help along the way, and we could do so much more. So contrast what happens with your compilers and interpreters when you make an error with what happens when you go to Google and if I misspell something, you get something better. And that's not because I had a formal grammar of every possible thing that the user could type, but it's rather because I've got a database of interactions. I said in the past, somebody typed this first, wasn't what they wanted, then they typed something else. So when when another person comes and types the first wrong thing, maybe we can suggest the second thing that everybody else got to eventually. So why can't our compilers do that, right? You know, 1 million poor students have forgotten that colon at the beginning of the if statement, but the compiler still doesn't know that. It hasn't learned anything from those 1 million failed interactions. But it could. We could save those, and we could say, hey, last time somebody typed something that worked like this, they changed it to work like this. I'm going to suggest that for you. Maybe I'll do it automatically, or maybe I'll just suggest it, but we should be able to work that out. Our compilers should have a database of misconceptions about the language and not just a formal description of the correct language. So one of my students at Stanford, Chris Beach, decided to do this. He didn't go into modern art. Rather, what this is a diagram of submissions to one of Andrew Ng's online classes, and each of these points is a program projected down into a 2-dimensional space and with the relationships between the programs. And the idea is he wanted to be able to summarize these and group them together, and then what he'd be able to do is say, well, if all these programs here are very similar, then I can have a TA look at, say, the centroid of this group, write a comment about what's good and bad about that program, and then we can apply that comment to everybody in that group. So how well does that work? So he was able to discover these kinds of things. So all these mathematical identities that you could have discovered with a computer algebra system, he discovered just by figuring out that these programs were similar to each other. And the results seemed pretty good. So we got up to 98.8% of the programs were covered. And so basically out of 50,000 programs, you only had to grade 500 of them or give feedback for 500 of them. And and then we could classify 98.8% of them, so we're doing 100 times less work than we had to do otherwise. So that seems pretty good. So the answer is yes, we can do that, and it works better as a human-machine interface partnership. So it's still place for a human in the loop, but a machine can do a lot of the work. So, machine learning as an agile software tool sounds great. I hope I've convinced you of something. Now, is there a catch? Well, unfortunately, yes. And here's another paper with an intriguing title: Machine Learning is the High-Interest Credit Card of Technical Debt. Right, so technical debt is this idea of you're developing your program and you're going really fast and you're cutting corners, and that's great because you get your first working version out, but then as you try to maintain it, things come back to bite you, and you have to go back and redo them in a better way. And the point of this paper is sometimes it's good to do that. You know, it's fine to have debt sometimes. If you want to live in a house, you take on a mortgage, and that's fine. You get some debt, but you get some advantage to it. But you should know when you're getting the debt and what you're getting into, and whether now's the time to take it on or not. And machine learning allows you to take on more of it faster than any other technique. All right, so what's the problem with machine learning? What type of debt or what type of problems you run into? So first is a lack of clear abstraction barriers. So if you have a traditional program like this and there's a bug somewhere, you can usually tell the bug's in this module. I can sort of trace and do all those other types of tricks, and I can isolate the bug to one place. If you have a deep learning network and it gets something wrong, you don't have any idea where the bug is. And it may not even make sense to say that the bug is in one place. Rather, the bug is distributed throughout the whole network. And you can fix one thing and this one instance will now be fixed, but then you don't know if another instance is going to be made worse by that change. And so related to that is changing anything changes everything. So like this pachinko machine, you move one of these nails up at the top, and then all the patterns of all the balls that fall down have forever changed. And so it's difficult to make corrections and predict what the results of those corrections is going to be. Okay, here's another thing that you get, it's sort of a failure of success. So if you're observing data, then you don't have this issue. You get some data, you run your program on it, and you get some result. But once you become a player in some marketplace, now there starts to be feedback loops. That you get some data, you publish your system, people interact with your system, and now they've changed and their behavior changes, and that changes you back, and you have to worry about that. So, we show search results, a lot of people use them. We can use your clicks as feedback. Maybe if you click on the first result, that means that result is a good one. But now there's this feedback loop that you're clicking on things because it's first, and it's first because you're clicking on them, and you have to be very careful about that because you change the world by acting. There's this problem I call attractive nuisance, which is when you create a machine learning resource, everybody wants to use it, and they may be using it for the wrong thing. Right, so I know we had this early on at Google. We created a set of synonyms for search terms. So you put in your search term, and we figured out what are good synonym words to add into that, and then your searches suddenly got better. And then the people over on the ad side says, oh, that's awesome. We want to have synonyms too. We'll take your database and we'll add them into the ad system. And all of a sudden it didn't work. And because the name synonym really wasn't right. They all looked like synonyms. You look at the database and say, okay, I got this word, what are the synonyms for it? They all look like synonyms. But what they really were words that you should add into a search query to make the search query better, which are not necessarily the same as words that you should add into an ad display to make the ad display better. And so there are times when you can share resources, and there are times when things that you look like you could share really are completely different, and you need to generate your own resources. And it's difficult to understand that. There's this non-stationarity effect, meaning data changes over time, and we always have to figure out what do we want to do? Do we want to stick with the current data, or is it time to update? How much of the past data do we want to use? It's coming up to Christmas. Should we suddenly count more things from exactly 1 year ago? And all these types of issues. And there's no clear-cut answers to how to deal with that. There's this issue of configuration dependencies. So I got all this data. Where did this data come from? Was the data always accurate? Has there been changes in other systems that affect the data that they were generating that I'm depending on, so that what I see today is no longer the same as what I saw yesterday? Is the data that I use in training different from what I run in production? When the system gets loaded, does it drop some of the data, and am I aware of that? So these are all issues to deal with, and we can deal with them. But I think part of the problem is the lack of tooling for this. So we have great tools for doing sort of standard software development. I showed you some of the unit testing tools and so on. And as an industry, we've built up a whole framework for that. But for these type of data tools, this is all brand new, so we just haven't built up the systems as much. We're not as used to using them, so we make more mistakes. I'll go a little bit faster. So all these privacy and security issues, I won't get into that. There's this issue of wide versus narrow interfaces. So when I showed you the interface diagram of the Java system, you tried to design a system so that as little as possible passes between one module and the next. And that can come back to bite you. So here's an example. So I couldn't get the exact picture, but you get the idea. So I got a Google Now card that says, I was in Boston, it says, depart now to return your rental car to Logan Airport. So this is great. It figured out what was going on, gave me this little map of exactly where to go to. So how did it do that? Well, I don't know exactly, but I'm imagining that the system looks something like this, that I had an email from Hertz, and some process that extracted an event from that, and it says the event has a time and a location, and I have a current location, and then somebody else planned out that route, right? And so you can imagine what each of these individual routines look like. So far so good, so close, and yet it also told me this. Time of travel, 23 minutes by bicycle. And that kind of makes sense because it was a short trip, and when I do travel, when I commute into work for about that same distance, I use my bicycle, and so it knew that. But it didn't really know what it meant to return a rental car. And the problem was that wasn't anybody's fault, right? So this extract event thing was just supposed to figure out what the event is, which is a piece of text, and the time and the location. They got all that right. So everybody did their job perfectly, and yet the system as a whole failed. And how could you fix that? Well, you could say, instead of this sort of nice software engineering approach to pass just the stuff you need to each routine, you could say, pass everything I know. Everything I know about, well, usually commutes by bicycle, but also everything I know about, well, when you return a rental car, you probably don't tow it with your bicycle. And we don't know how to write systems that pass everything and still keep them maintainable. So, are there catches? Yes, there's many. Oops. But I'm going to paraphrase Winston Churchill when he was talking about democracy, and he said it's the worst form except for all the others. And so I think that's true for machine learning as well. So there are all these issues that are going to kill you, but I don't see any better way to do it. So I hope that in the future we can have more machine learning in software engineering, and we can figure out a way to solve all these problems. All right, thank you.
Well, thank you. Thank you, Peter. And I don't know if my mic is not loud. Thank you, Peter. And as our tradition, we have some time for question and answer. So I'll walk around with the mic, and everyone, please, take advantage. Some wonderful person you can ask some questions to. So let's take 5 or 10 minutes and have a question and answers.
Thank you so much for the great talk. I really enjoyed it. So I have one follow-up question. So like for a lot of tasks that we use deep learning, it's kind of like predicting the outcome. We don't know really, like for example, how a human talk in a language. We don't know really the generative model out of it. But for the programs that you mentioned, we kind of know the generative model, and we can actually like write another program that keeps generating programs for us. So my question is that how can we take into account this knowledge or take advantage of this fact and like improve the model?
Yeah, I guess we don't really know how to do that yet, right? So we know how to write programs, we know how to replace module the programs with training them with learning, and we know how to do the whole end-to-end bit, but I don't think we quite have the mechanism for how to combine them properly. And I think that's part of this software engineering discipline, is saying how can we take these pieces and compose them in ways that make sense. And so far we don't have that. You run experiments and you get it wrong and you try it again, and there doesn't seem to be much continuity between one experiment and the next. I'd like there to be pieces that persist a little bit longer and say maybe, well, I'll take a little bit of this and a little bit of that and combine them. Hopefully we can get there.
Next question?
You mentioned that actually you're going to talk more about the chess player, Korean chess player.
Oh, the Go player?
Yeah. So I was just wondering if you could, just tell us the story about what you think about how the machine, I guess, you won twice.
It's, 3 out of 4 so far.
Yeah, 3 out of 4.
Right. So it's fascinating. So in some ways, they did just what you thought should be done, right? So there's nothing exceptional about it. You can read the Nature paper and say, yeah, that's what I would have done if I said I want to write a Go playing program and I want to use deep learning. So they start off by using all the examples they had. So every board position and move by an expert player, the whole history of every recorded game. So fed that in and tried to learn 2 separate mappings using these deep learning networks. So one is a mapping from board position to where would a human play. So if I see a position that looks like this, I put down a stone here. And then second one is a mapping from a board position to what's my probability of winning. So did that based on the games that I'd seen before and being able to generalize. And then started saying, okay, well now we want to improve. And I think the key point here was getting to the point where self-play was actually useful. Right, so they were able to build the system up to the level where it was at an expert level, and it was better than any existing Go programs. So you could say, well, anybody else could have done this with an existing program, but for an existing program, if it played itself, it really wouldn't improve because it just was so far below where the top players are. And I think it's like, it's like compound interest. If you can get to the 1.1 rather than 1.0 or 0.9, then you multiply compound and then you start to take off. And so it's just crossing this threshold thing, just good enough. Now you can start playing yourself and take advantage of having a lot of computers, and you play a lot of games. So now you have, in addition to this, every game that a human has played, you now have meaningful self-play games. And so there was so much more data available to them because they were able to pass this threshold and make self-play work. And then the other thing that differentiates it is they were able to actually build this evaluation function that says how good is this position on the board. And nobody else has been able to do that before. So in the past, 10 years ago, none of the Go programs were any good at all because they really couldn't evaluate a position. They couldn't say who was winning. And then a sort of trick to get around that was to say, okay, we can't tell who's winning, but let's play the game all the way to the end and see who wins. Because at the very end of the game, now you can count and see who wins. And if you make reasonably good choices along the way, then you get a good answer. You're not guaranteed of making reasonably good choices along the way, so you play it out 1,000 times in average. And that works kind of okay. That's an okay estimate of how well you are. But if you can then feed that into a network and have a kind of static evaluator that says, right now, without having to play out, I have an estimate of how good this move is, that allows you to move so much faster. And now they still use these rollouts, they still play all the way ahead, but they have the advantage that they can focus in on the moves that are actually moves that are worth trying, and nobody else was able to do that focus before. And so I think that's what made the difference. And I guess the other thing is, Go has been held up as this game that's, well, it's so much more complicated than chess, it's so difficult, it takes human intuition and so on. But remember, it's still a perfect information, finite, discrete game. So it's not surprising. I mean, this should be exactly the kind of thing that computers should be better than humans at. And it took us a while to get there, but now they're there, and by next year there'll be no question. So even if Lee comes back and wins the second one and only loses 3-2, and there's another Go champion, and maybe he could win, but in a year or two from now, it'll be all over. The same way as in chess, in '97, it took an IBM supercomputer to beat the best human player. But now, you can get a program on your laptop that'll destroy any human player. And so it's going to be the same thing for Go.
So I have a question.
The next question, the questioner is also, could you just quickly introduce yourself before you ask your questions, so other folks know who you are and maybe where you're from?
Hello, Russell Howe from Applied Invention. My question is a little bit about some of these fundamental tools you were talking about. You talked about logging and tracing and asserts at the beginning for traditional programming. And then in deep learning, we have sort of things like Deep Dream that give you a little bit of insight into what the network is.
Yeah.
So where should we be looking for the sort of fundamental tools for that, the sort of the oscilloscope and the multimeter of a deep network?
Yeah, that's a great question. And Deep Dream and sort of all the image processing things have this great advantage that you can look at an image and see what's going on, right? And so you can look at any level and say, that looks like a line detector, and that looks like an eye, and that looks like a face, and it's interesting that those go at one level after another. And that's great for any two-dimensional data. Things like speech recognition is similar, so you can deal with that. But in other domains, you've got 100 or million-dimensional data, and there's no easy way to depict that. And that's true for deep learning, it's true for every kind of learning. So we can try to project down to lower dimensions and show some sort of picture, but it's going to be a shadow rather than the real thing, and it won't have the immediacy. So the other thing about two-dimensional pixels is you can look at it no matter what. I mean, you may not understand it perfectly, but we have some intuition of, I see what this is. And if you take two other dimensions, principal component analysis, and plot those, I don't necessarily know what that means. So I don't know the answer to that. And then we got to have better experimental frameworks of how do we run these systems, how do we tell what's our percentage, are we improving, is the world changing over time, can we have, we have like persistent build systems now where every time there's a change, we build and we run all the tests and make sure everything's okay. We want to do that for our machine learned systems as well. And I think that's hard, in part because you often have online data rather than batch data. And so every time there's a new piece of data, what do? So I say, am I going to run all my tests every time I get a new piece of data? What if I'm getting 20,000 pieces of data a second? I don't have time to run all my tests. So do I batch them up? Do I have alert systems that say, things look a little bit different than they were yesterday? And you see that a lot, right? So a lot of people are trying to use learning techniques for things like network security. And there you accept a certain level of false positives, where it says, hey, something different's going on. Somebody should look into this. The system isn't smart enough to figure out if it really is something to care about or not. But it can say this is a little unusual, and then somebody has to dig in farther and figure out what's going on. So I think for a long time we're going to have that. So, long term, I'm worried about automation leading to unemployment. But for the next decade or two, you guys are all good.
All right, on to the next question.
Hi, I'm Steve McInerney from Microsoft Azure Machine Learning. When you talked about the progression transition from supervised to unsupervised learning, and you're saying there's no explicit cost function. So what can you say generally about, eventually you just get at some, structure for representation of all knowledge. So if you're trying to, represent knowledge from, let's say, all Google Now users or something, what sort of work is there on meta learning of optimizing those data structures?
Yeah, so I guess a lot of things to say that. One is, to what extent do we distinguish data for particular tasks versus overall global models, right? So there's a particular thing you want to do. I want to show this alert under these circumstances, and I can measure how well am I doing on that task. But I'd also like to have transfer learning from one thing to another. So I'd like to have kind of these global models that are useful across multiple tasks. And we've identified now that there's this field of transfer learning, and we have some sort of results with it. But I don't think we have best practices yet of how to build these models, what gets shared and what doesn't. When are you better trying to take a model that's already been built and adapt it to your new problem versus start over from scratch? We always have these discussions, and I think it's done by intuition now rather than by good theory behind it. So I think that's a great area to work on.
Okay, so then we have time for one last question. So, you ready?
Introduce yourself.
Okay. Hi, thanks for the talk, very inspiring. So I'm Lei, and right now I'm working at a startup called Clary, which is focused on sales, predictive analytics, and forecast. So we are using some of these machine learning tools, and a general question about this like deep learning and human intelligence is that it feels like all these machine learning are not very data efficient. Just take AlphaGo as one example. It probably trained over like tens of millions of games. But for human beings, like human players, they were trained by like thousands of games. Then they can already achieve almost like the top professional level. But for machines, of course, it can learn way much faster, but it requires so much more volume of data to learn. Mm-hmm. So what do you think about that?
Yeah. Yeah, I think that's certainly right, and in some sense, it's like looking for your keys under the lamppost. That we say, well, where do I have a lot of data, and I'm going to focus on that because that's what we know how to do best. I think a lot of this relates to the previous question of doing transfer learning, and so I think the reason people are so good at learning from a few examples is because they've already learned a similar thing before from some other examples, right? So you talked about Go, but I'm going to talk instead about the Atari game playing. And there we've got criticisms like people say, oh, well, if you flip the color channels, so inverted red and blue, then the system's performance goes back to 0, and it has to learn all over again. And so it said, that's really dumb because for a human, if you change the color of the things, the human would know that right away. And I think the answer to that is, well, yeah, but that's because the human did two things. First, we learned how to see. We did that when we were small, and then we learned to play Atari games some number of years later. Whereas the computer, in this case, was learning both of those things at the same time. And that's probably a mistake, right? Probably we should have said, first, let's train a system to see, and recognize objects and so on. And now, once it's done that, now we'll show it the Atari games. And then it wouldn't have any trouble saying a red blob is the same as a blue blob, it just happens to have a different color. But if instead you say, well, here's 3 inputs, they don't necessarily have anything to do with each other. If we change one for another, why would it think that those were representing similar things? But it has to learn that on its own, because it doesn't have an idea that what it's learning is vision. It just says what I'm learning is a mapping from inputs. So if we can get to the point where we have these kind of general purpose stuff, I know how to see, I know how to recognize language, I know how to navigate and move around and so on, and I've got all that built in, and now I can apply it to a new domain, then I think you'll see learning with much less data. But when you have to learn everything from scratch, then it takes a lot of data.
All right, let's thank our speaker, and thank you very much. Peter Norvig, for bringing that and talking to us tonight.